Right, afternoon everyone. This is a picture that I particularly like, and I normally start with my lectures one, because it gives us it was one of the first pictures taken by Apollo 17 of the whole world without any shadow on it. And secondly, as you can hear from my accent, it happens to show a very beautiful country down in the south of Africa here, where you saw the pictures of the cheetah and Havana, who caused rather what I would call a lovely spectacle last Friday. The area I'm looking at is basically looking at sustainable energy vehicles, and I'm going to concentrate mainly on light car because that is one of the projects which is the furthest developed. And I'm going to be talking mainly about some of the areas that we've been involved in at Oxford University and how that carries on. I'm a part of the electrical power group, and I'll introduce some of the other characters that we are in the group in a moment. One of the questions that always people start asking me is, what do I mean by sustainable energy? And I take a variation of the Brundtland report, which basically says, can we meet the energy needs of today without compromising the energy needs of tomorrow? And that's one of the key drivers behind a lot of the projects that I'm involved with, including those in the transport sector. As we've already heard in many talks today, a lot of the issues are that the transport sector is one of the few energy sectors which is dependent exclusively on oil. Basically, things like electricity have got multiple sources coming through. Transport, by and large, has only one source, and that's its dependence on oil. And this has caused a lot of concerns amongst the EU and in the US about energy security, also issues about climate change and the impact of the increased amount of carbon dioxide that's produced. And also, there's a slow concern coming in about the oil reserves that are available. Although one has to say, every time I go and look up the amount of oil reserves, they keep on increasing, not decreasing. So we've got to watch that one. This is one of the interesting and scary slides that I use, and this is one from the BP, which shows the total energy consumption that the world uses from 1980. In 1980, you can see that we're using probably about 6,500 million tons of oil equivalent each year. And what you've been noticing over the years, our energy consumption has been increasing despite all the concerns. In 2005, we're just going over 10,500 million tons of oil equivalent each year. If you look at the green one, which is the bottom one, that's the amount that we're using in oil, and you can see that one is increasing, not decreasing. Also, the top one is coal, and that's been increasing. One of the scary statistics for me was between 2003 and 2004, China's energy usage went up 15% in 1 year, which resulted in a 5% increase in the world's energy growth. So we have a problem. The amount of energy that we're using is going up, despite everybody's concerns about climate change and the end of oil. Now for a weird question. Which mammal has the least DNA? You might want to think about it. And if you're talking to somebody, you might want to say, hi, I am, and I think the animal is. So if you want to just spend a couple of seconds, talk to the person next to you, and what animal do you think has the least DNA? The bad news is, the next slide does not give the answer. I'll let you think about that. By the time we get to the end of the talk, we'll get there. This is basically some of the members of the group that are involved in sustainable energy. About 4 years, I moved into it fairly recently. About 4 years ago, I had one person involved, which was Tim. Last year, about 4 people involved, and this coming year, about 10 people involved. So what's very interesting to me is that the young people are really interested in getting into sustainable energy. One of the large focus areas we're looking is in the transport sector, but we're also looking at domestic sector and renewable generation. We started off a number of years back looking at the BFC ECHO, which is a project which is to look at what is the envelope to which technology can push in terms of energy efficiency. And as you can see there, we achieved a reasonably respectable 5,500 miles per gallon equivalent in petrol. This is a fuel cell-based vehicle, and it uses around about 25 watts to do about 25 kilometers per hour. One of the downsides, though, is that if you look from the driver's point of view, you can see it's rather cramped. And somebody my size will not fit into this vehicle, and therefore it's not a practical vehicle, but it does start to give a show of what is actually achievable. And one of the early talks, remember, we talked about weight, and weight being an important thing, and this one definitely shows that weight can actually give you quite incredible advantages. Clue. Small DNA in cells results in small blood cells. Okay, so that's a clue, and you might think why that might be important. This is just a basic SWOT analysis on hydrogens. It's a very simple one. A lot of speakers have been talking about it, but just some of the highlights is to say that it's got a high energy density if you look in terms of mass, but a very low energy density if you talk in terms of volume. And that's one of the issues we talk about. BMW talk about going to liquid hydrogen. Main advantage of hydrogen is that there are many routes to hydrogen. It's a secondary carrier, and therefore there are different routes that we can use to produce hydrogen. And therefore, from our point of view perspective, it's useful as a transient energy source, because if you put the infrastructure now, we can move from methane type production through to alternative, more cleaner production in the future. But as we've been talking about, infrastructure development is a real problem. One of the strengths is that hydrogen is very light, and so it rises. So that means in terms of safety issues that if you have any leaks, as long as you design your vehicle correctly, most of the hydrogens that rise and get out of the system. Whereas if you look in petroleum, the problem with petroleum gases is that they sink, and therefore you're more likely to have accidents with petroleum. Of course, the biggest bugbear with hydrogen is the Hindenburg, and the public perception of safety means that there's going to be an issue, there's a barrier there that's going to have to be dealt with. Also, another severe weakness is the cost, and therefore one of the things we've been looking at in the LifeCar project is to say, how can we minimize the cost of the overall vehicle? Again, a number of opportunities in that we can diversify the energy mix in the transport sector. There's going to be opportunities in looking at developing new storage techniques, and already we can see that other competing areas are going to be battery technologies and biofuels. The LifeCar is a collaboration between 6 different partners. There's Morgan, who's actually producing the car, Cranfield University, that's doing the controls and the simulation, Linde BOC are providing the hydrogen refueling infrastructure, Kinetic are doing the fuel cell development, Oscar have been doing the system integration and some of the mechanical design, and we at Oxford have been looking at the powertrain from the fuel cell to the wheel. Very simple and crude picture which gives you an idea of what the car actually looks like. It's a 4-wheel drive, so each wheel is actually independently driven. We have a converter that converts from a very high voltage, 300 400 volt bus, which I'll talk about just now. We then have a hydrogen fuel cell sitting there together with the regulators and the storage tank. One of the things is that Hugo mentioned, it's a network hybrid, and that means that we also have a bank of ultracapacitors which supply the power requirements. So one of the beauties of this car is that we separate out the energy requirement for the cruise from the energy requirement to do the acceleration. So the energy from the acceleration is doing that side. To give you a comparison, the fuel cell size is only 20 kilowatts, but we can do 0 to 60 in about 7 seconds. Okay? And the reason for that is that our power source is sitting in the ultracapacitors, not in the fuel cell. So that means we can actually separate the two out, and therefore we get some tremendous benefits from that particular system. Also, we said that cost was an issue, and the cost is behind the fuel cell means that we can get away with this with a much smaller fuel cell, and therefore it becomes cost effective at the moment. Also, the car weight is targeting around about 650 to 700 kilograms, and that size tank we're getting away with a much smaller tank of about 60 liters at 350 bar, with a range of about 300 miles. The area we've been looking at specifically is looking at the development of the electrical machine motors. And what we have here is just an explosion of what the motors look like. We have a central stator area here where we have the coils which are wound around powdered iron materials, and we have our brushes, we have our permanent magnets on the stator, and those together provide the motor power. We've done an extensive analysis. One of the particular problems that we have with this project is that it's got when you look at the urban cycle, is that you have high powers during the acceleration, but during cruise you've actually got something like 10% of the power that you actually require. And therefore one of the key issues for us was to be able to optimize so that we don't burn the motors out during acceleration, but we also have very high efficiency during the low periods. So we've done quite a lot of work in optimizing those two constraints. This is how we actually go about making it. As I said, one of the interesting things is that this is the iron core component that's actually made out of a press-sintered iron material, which is very cheap and easy to make. They're actually pressed materials, there's no machining involved in that. We then wind the copper winding around that, so it's a very simple and easy winding to do compared to most electric motors. And then we mount this not on a steel base, but actually on a carbon fiber base or a composite base. And so therefore we can get away with having a motor which produces 50 kilowatts, which only weighs about 12 kilograms. Okay, so that's quite it's a very much lightweight machine compared to normal ones. This shows us actually the assembly process where we actually bring together, this is our motor here, we can see there's our stator windings in the center there, and there are the two magnetic rotors in there. And this is part of the assembly process, and we bring the casing on the mild side and we just left the motor in the center. That then gets integrated into the wheel, and one of the decisions that we made in our whole system design was to say that rather than going for wheel hub motors, we'll actually go for off-board motors, and we'll then have a short stub shaft and integrate that into the system. Hugo was involved in actually designing a whole new suspension system so that it could actually, the whole system could actually manage and fit in that. I talked about that we're actually working on effectively a hybrid system, and this is quite a good way of showing why we want to do that. If you look at, we've got a graph of power density on this side here versus energy density sitting on that side. Then we see the fuel cells are sitting way up there. They're very energy dense, but not very power dense. Ultracapacitors, which we're using, have a lot of power but not a lot of energy. So mixing those two together, we actually get an overall system which optimizes those two components, and therefore we can achieve a much better overall vehicle characteristics. The ones that we're using is similar to this one here, which is done by Maxwell, and one of the advantages is that we're now getting a 3,000 farad battery in something the size of a Coke can. One of the key things when you look at ultra capacitors is that you've got to make sure that the equivalent series resistance, or the ESR, is very low, because if you're drawing a large amount of energy out of that, you want to make sure that your losses are reasonably small. We're looking to develop about 150 kilowatts from these guys. The discharge current has to also again be very small in terms of overall efficiency, and that shows you what the energy and the power density is sitting there. One of the other curious things that we've done in the vehicle is that we've actually got a floating bus. Our DC bus is not kept fixed, it actually varies between 300 and 400 volts. And this this means that the capacitor is directly coupled to the bus, and it means that we no longer have to have a DC-DC converter, and therefore we knock out quite a large amount of losses, and therefore we have a much more efficient system. The downside of that is that the control for the motors becomes a little bit more complicated because you don't have a fixed DC voltage coming in, you rather have a variable voltage that we have to deal with. But we have the advantage of a much more improved system efficiency. The answer to the weird question is it's the bat. And the reason for that is that in the bat it has to be able to fly, and it has to supply energy to the wings, for the wing muscles, and it needs to have very small blood cells in order to do that. And this is a demonstration of an animal which has been designed for a very specific and challenging task. And it's been designed in the sense that if you look at our DNA, something like 20% of our DNA is actually waste DNA. It's something that we've accumulated over the years. In the back, there's almost 0% wasted DNA. And what this tries to tell us, the reason why I brought up this weird question was to say you have to look at a whole system development for fuel cell vehicles if you really want to be able to push the envelope. So the light bar at the end of the day is something which is going to be reasonably high performance. I said 0 to 60 in about 7 seconds, 300-mile range, very low weight. It has a reasonable range, and it's been well system engineered. Just to show you, to cut away, that's where the ultracapacitors are going to be sitting in the central wheel. We've got the fuel cell sitting here, and the particular motors are sitting over there. This car will also have quite a large boot, and so we don't compromise on that. Thank you very much.